Welcome back to CET3136. This is Logic Devices Programming. This is Professor Evans, and in this lecture, I'm going to go over finite state machines. So, a finite state machine, or FSM for short, is a sequential system. It's a digital system whose outputs are a function of both its present input values and its past history of input values. For example, if you've ever built a counter, you've built a finite state machine. It is a way that we can interpret any sort of sequential logic, and it's a system or a methodology that we can use to implement any kind of sequential system, basically a system that deals with memory or past history, and that has some sort of logistics that is required to implement it. So for example, if you think about the controllers that we might design to control an elevator, the way that air traffic control works, the way that we have to logistically figure out ways that planes will land and take off safely. If you think about traffic lights and the logic that is required to implement a four-way intersection. If you think about a coin or badge operated turnstile, how you may have to deposit money if you're going into the subway, or you may have to swipe a badge in order to get through a turnstile or a locked door. These are all systems that can be implemented with a state machine. So the purpose of this lecture is to discuss what a state machine is and how we would construct one for a sequential system. So there are two kinds of state machines. You can have state machines that are synchronous, meaning they are controlled by a system clock, and the output state will be changed only at a triggering edge. Or you can have an asynchronous finite state machine where the output changes when the inputs change. For this particular lecture, we're just going to focus on synchronous systems. So as we begin to understand what an FSM is and what it does, the first thing that we're going to look at is a block diagram that explains how a state machine works. If you look at the diagram on the screen, you'll see a couple of blocks. The first one is the combinational logic block. We have a state register, a clock, and then we have some inputs and some outputs. So first I'm going to go over sort of how this is constructed and how this represents a state machine. And the first thing that we have to understand about any FSM is the idea of state. The condition of the system as defined by its past inputs is known as the state. So for example, when you have designed counters in other classes, we identified the mod number of a counter by counting its unique states, its unique output states. So any unique output is going to be a particular state of your FSM. State is stored within the state register, which is right here, and it is assigned a unique binary value. So state can be 0 or 1, or it can be a vector of zeros and ones. And each state will have a different meaning depending on the circuit that you're trying to design and the output that you're trying to produce. So a finite state machine's present state provides all the information needed about past history to determine its current output and the next state. So with the state machine, one of the things that it does, and one of the things that makes it different from other types of digital circuits, is the idea that it calculates a current output based on a present state, and it also determines what output should come next when the next triggering clock edge occurs. And that's why you see both a present state and a next state listed on this diagram. So the present state is what provides information to this combinational logic block. This logic block will take the present state as well as any inputs from the user and then determine what the output should be next. The combinational logic block will also determine what the next state should be once the clock makes a transition. So the present state is also a binary value. It could be a 0 or 1, or again, a vector of zeros and ones. It all depends on your application. But the present state is what is used along with the inputs to determine what the output should be. So for example, if you are designing some sort of system to control an elevator, the opening and closing of a door, a garage door system, a turnstile system, a check-in system for a hotel, for an airport, etc., you're going to decide what should happen and what kind of output you should have based on any user inputs and your present state. The outputs are going to be computed by the combinational logic block right here. The external inputs could be anything. It all depends on your application. So for example, if you were designing a system to control an elevator, an input would be the user pressing a button. If you were designing a system that maybe that had to be enabled or disabled at some point, that input would be one of the inputs that is listed here. And then the other thing that the output depends on is the present state. So the state registers outputs, provide the present state to our combinational logic block, and then the outputs are determined based off these two values. The combinational logic also computes the next state. It determines what should happen next after the current output. So, for example, in a counter, we know that depending on whether you're counting up or down, maybe you're counting by 2s or by 5s, it doesn't really matter, but we know what should happen next based on the design of our system. So the combinational logic will determine the outputs as well as determine what's going to happen next. At each triggering clock edge, the new state or the next state value is clocked into the state register right here. And it will become the new present state value. So before we can start to actually build an FSM in VHDL, we first have to have a state diagram. So I'm going to explain through a couple of examples using some flip-flops what a state diagram looks like. So if you think back to a D flip-flop, a D flip-flop typically has one user input, which is your D input, your data input, and the output of that flip-flop will be Q, and Q will either be high or low, depending on what D is when the clock makes a transition. Now, the first thing I want you to notice with any state diagram, we're always going to have some sort of clear or reset input. We're always going to need that when we design a finite state machine, because this is the way that we initialize the machine. We have to have an initial state, a place to start from. So regardless of any other inputs that might be coming into your system, one input you will always have is some sort of reset. When that reset is activated, that allows us to begin in an initial state. So for the purpose of this diagram, we're going to assume that when clear bar is active, we begin in this state right here. So with this diagram, we have two circles. This is a state. This is another state. When I'm in this state, the output is 0. When I'm in this state, the output is 1. The way that I move from one state to another is by the input D. So let's say that I activate clear bar, I pulse that low. I'm going to begin in this state. If the user to this particular flip-flop, if the D input is a 0, I'm going to stay in this state where the output is 0. If the user supplies a 1, so D is 1, I move from this state to this state here where my output is now 1. If D continues to be a 1, I stay in this state. Or if D is a 0, I go back to the first state. So with this state diagram, some really important things that have to be shown are the different states that are available, how we move from one state to another based on inputs, and the fact that we have to have a clear or reset to get us into our initial condition or our initial state. Here's a diagram for an SR flip-flop. Again, we have two states for a flip-flop. Either the output is high or the output is low. So that's represented with our two circles here. And you can see that I can only move from the first state to the second state when S is 1 and R is 0. That means I'm setting the flip-flop. And if I were to have an input where S is 0 and R is 1, that's a reset to the flip-flop, and we move back to the first state. We can also see within this state, if the output is 0 and set is a 0, that means I'm going to stay in this state. If I'm in this state where the output is 1 and reset or R is 0, I'm going to also stay in this state. My third example for a state diagram is for a 2-bit shift right register. Notice if it's 2 bits, that means I'm going to have 4 possible states, 0, 0, 1, 0, 1, 1, or 0, 1. Those are my 4 possible states. I have the clear bar input right here, allowing me to initialize the state machine and begin in our initial state of 0, 0. With the shift right register, you also have a user input. In this case, it's called SI. So this input will be supplied from the user. If you begin in state 0, 0, where this is the output, if a 0 is supplied, we're going to stay in this state because you're shifting in a 0. You're going to shift right, and you're going to have the same output. From this state, Si could be 1. If you shift in a 1, this is your output. Your output is now 1, 0. And you can see that from this particular state, we have two options. If Si is a 0, we go here. If Si is a 1, we go here. So a state diagram is going to show, once again, every possible output state for your design. It's also going to show every possible option based on your inputs. So you'll notice with each particular bubble, I know what's going to happen if my single input, Si, is a 0 or a 1. Every single one of these states has those situations covered. So a state diagram has to clearly depict the inputs and how the inputs affect moving from one state to another. You have to cover all of your bases. You have to make sure that all input cases are covered so that it's very clear to know what state you're going to be in no matter how the input changes. So now that we've discussed state diagrams, I'm going to show you our first example of a state machine, and I'm going to start with a simple counter. A simple counter is a special case of a state machine without inputs, except for clock and reset. Clock and reset are considered sort of your default inputs. Every state machine is going to have a clock. Every state machine is going to have a reset to initialize the counter. Beyond that, you could have other user inputs like data inputs, enable inputs, or other things depending on your application. But with a counter, or at least with a simple one that doesn't require enabling, it doesn't require the user to determine whether it's counting up or counting down. We're just going to start with a very basic 2-bit counter. And in that scenario, you don't have any other inputs aside from clock and reset. So this is sort of an updated diagram for a FSM for a simple counter. You can see that the combinational logic computes the next state based on the present state. The next state is stored in the state register. When the clock makes a transition, the next state becomes the present state, which is fed directly to the output. At the same time, the present state is used within the combinational next state logic blocks to determine the next state that is stored here. This is the basic idea behind a finite state machine for a very simple counter. So when we have a state diagram for a counter, like the one we're building here, we're going to show each state. And in this case, our arcs are unlabeled, meaning that there's no input from the user that causes a transition from one state to the next. We're automatically going to transition from one state to the next on each clock pulse. So these are unlabeled, showing an unconditional transition. Every time the clock makes a transition, we will transition from one state to the next in this pattern. This arrow here represents your clear to initialize the state machine to the initial state of 0, 0. Once you have a state diagram, you can move on to making a truth table for your finite state machine. In this case, our truth table shows the present state and then the next state. So you'll want to have both a diagram and a truth table for design as well as verification. When you're done with your design and you're actually testing it to see if it'll work, you'll ultimately be comparing it back to your diagram and your truth table. So within our table, we can see that when the present state is 0, 0, the next state should be 0, 1. The present state is 0, 1, the next state should be 1, 0, and so on. We can clearly see that this is going to be a 2-bit counter that counts up from 0 to 1, 1. Now let's take a look at the code we would use to implement this idea of a 2-bit counter as a state machine. Yes, we've already talked about other ways to implement a counter. This particular example is focusing on how do we implement it as a state machine. So let's start with our entity. Within the entity, we have our port statement that defines the inputs and the outputs to the state machine. In this case, we're going to have clear and clock. Remember, within the context of our class, if you're building a finite state machine, you're always going to have a clock, you're always going to have a clear. We need those two things because we're building synchronous machines, so therefore you need a clock, and we need the clear as a way to initialize the machine to an initial state. The other thing we have is an output called count. It's a vector 1 down to 0, so there's our 2-bit output. And that's our entity. Next, we're going to have our architecture. And within the architecture, we're going to have a few new things that you probably haven't seen before. Start by looking at the first line below architecture. We have the word subtype. Subtype state is standard logic vector 1 down to 0. What we're doing here is we're defining our own type. Instead of defining something as an integer or as a signed number or an unsigned number or a signal or standard logic vector, we're creating our own type. And we're going to call that type state. You can call it any name you want. We're going to use the word state because we want to define each state of the counter. In this case, since we're building a 2-bit counter, your state will only ever be a 2-bit number. So state is defined as a standard logic vector of 1 down to 0. Then we're going to define the present state and the next state as signals, and their type is going to be of the subtype we created. Beyond that, we have 4 constants. Each one of these constants will represent a single output state of our counter. These names can be anything you want. Logistically, it makes sense to name each state based on the output that's going to be derived from that state. So we have state 0, state 1, state 2, and state 3, representing our 4 output states. Notice that the constant is of type state. Again, that goes back to the subtype that was created right here. Since this is a vector, we can assign a 2-bit value to each one of our constants. Why am I doing all of this? Why not just use zeros and ones? Why am I giving a name to all of these combinations? There's a reason why we do this. When it comes to building a state machine and any other sort of complex code, you want to be able to use signal names, constant names, variable names as much as possible and avoid just hard coding ones and zeros. This makes your code easier to debug when it doesn't work. This makes it easier to test. This makes it easier for someone else to read your code and know what's going on. Later on, we're going to refer to something like state 0. For example, just take a peek down here. We're going to refer to state 0. Now, you could totally, instead of writing the word state 0, you could just write the binary value 0, 0. That's fine, but actually giving this state a name makes it easier to understand what's going on. Because you can have many different types of FSMs with many different types of outputs, and those outputs will all mean something different depending on the machine you're building. We don't want to hard code values as much as possible. So we're setting all this up to create a system where our code will seamlessly explain what we're doing. And you won't have to stop and ask yourself, what does that 1, 1 mean again? Why is this 0, 1 right here? Giving things a name within a state machine makes it easier to comprehend, makes it easier to code, makes it easier to debug, makes it easier to troubleshoot. It also makes your code more dynamic. What if I want to change this counter that instead of it counting from 0 to 1 to 2 to 3, what if I want it to count down, for example? Then I can come in with a few simple clicks and make state 0, 1, 1, make this state 1, 0, make this state 0, 1, make this state 0, 0, and the rest of my code can remain completely unchanged, and it will count down. That's very quick and easy. If you actually hard code every time you use your output states, you've got to go and find every time you typed one of these in, and you've got to go manually change it all over your code. This is why we use this style. It makes your code more dynamic and makes it easily adaptable to other situations. So if we define our states up here and use constants in this case, as we write our code later on, I can easily change state 0, state 1, state 2, and state 3 to be anything I want. And this finite state machine will be able to adapt very quickly. So that's why we have this piece of code up here. So next we have the beginning of our architecture with a first process that is just going to respond to the clock. Notice that if you have a rising clock edge, then we'll check to see if reset is 1. If reset is 1, we're going to set the present state of our state machine to 0, state 0, which would be an output of 0, 0. So as soon as the reset button is activated, the present state, and thus the output of your counter, will be state 0, 0. If reset is not set, then we're going to set the present state to the next state. Keep in mind, we haven't defined what the next state is yet. That's coming in a second process. This first process represents the state register of your finite state machine. When the clock makes a transition, it transfers the next state to the present state, and that's going to become your output state. Our second process right here controls the outputs of our state machine, our counter in this case. We have a sensitivity list with just the present state. So basically, this process is going to take action when there's a change in the present state. We have a case statement where we're going to look at the value of the present state and determine what the next state should be. So when the present state is in state 0, the next state will be state 1. When the present state is state 1, the next state will be state 2, and so on. Notice that I cover each state, showing what should happen next. And I even have a when others statement, stating that if something should go wrong, if the counter gets out of sequence or anything like that, return to state 0. At the end of my case statement, this is where we actually control the output. The output is defined as count if you go back to the port statement. This is the output we're actually going to see. And here's where we store the present state in count. So this process here controls the next state, what the next state will be based on the present input, and it will also send whatever the present input currently is to our output. If you were to simulate this code, here's what it might look like. Notice we have our clock signal. We have our reset. The reset is active high in this picture. I will say that that contrasts with the name given right here. So this is an example I got for the book. I'm realizing that they should have either called this clear or they should have made the clear active low. But for the purpose of this example, it's fine. So in this case, the clear is actually active high. So with this positive transition right here, the present state is set to be 0, and the output is based on the present state, so it is also 0. The next state is determined to be 1. On the next positive transition, we see the counter beginning to count. The present state goes to 1, the next state goes to 2, and our output count is based on the present state. And that's basically your 2-bit counter as a finite state machine. So in general, there are 2 types of finite state machines. There's the Mealy machine and the Moore machine. The Mealy machine is a machine where the outputs are a function of both inputs and present state. With the Moore machine, the outputs are only a function of the present state. I'm going to show you some diagrams to hopefully make that a little bit clearer so that you can understand the difference between the 2. A Moore machine is conceptually simpler. Typically, at first glance, when we begin to create an FSM, the Moore machine is the one your mind is naturally going to tend to go towards. It's very straightforward. But it typically requires more states than a Mealy machine. Which one you use is dependent on the particular project you're working on and how important it is to minimize the number of states. So there's not one that's better than the other. It all depends on your application. But generally, the benefit of a Mealy machine is you have less states. The benefit of a Moore machine is that it's conceptually simpler to implement. So the diagram I showed you earlier was actually the Mealy style for showing the logic of a finite state machine. Notice within the combinational logic block, the outputs depend on the inputs and the present state. And if you look at our definition, outputs are a function of both inputs and present state. So that's your Mealy machine. A Moore machine actually separates the combinational logic into 2 blocks instead of 1. So you'd have one block that only determines the outputs based on the present state. So the outputs are only a function of the present state. It has a second combinational logic block that determines the next state. And the next state block takes the inputs as well as the present state. To determine what the next state is, it's stored in a state register. When the clock makes a transition, the next state becomes the present state, and that's fed to the outputs. So these are your block diagrams of a Mealy machine and a Moore machine. Here are two state diagrams that show the differences between a Mealy and a Moore. So this is a sequence detector. The output is high when 2 or more ones are detected. Let's start with the Moore machine on the right. Notice we have 3 states, A, B, and C. The output for each state is shown within the bubble. The output for each state is shown within the bubble. So let's assume that I begin with a reset to initialize the finite state machine, and I begin in state A. If the input is a 1, I go to state B. If the input is a 0, I stay in state A. So let's assume that the first 1 is detected. I would go to state B. I've only detected one at this point, so the output is 0. But once a second 1 is detected, we move to state C, where the output is now 1. And if I continue to detect more 1s, I'll continue to stay in state C, where the output is high, showing that I've detected a sequence of 2 or more 1s. As soon as the input goes low, I leave state C and go back to state A, and I'm back to where I started. With a Moore machine, the output is shown within the state bubble. And the only thing that you see on the arc are the inputs that would cause you to go from one state to another. So remember, the definition of a Moore machine is that the outputs are only a function of its present state. That's why the output is shown within each state bubble. The output is a function of the present state. Now look at the Mealy machine on the left. First thing you should notice is that there's only 2 states, A and B. And there's no output written inside the bubble. That's because a Mealy machine has its outputs as a function of present state and the input. So with the Mealy machine, it's labeled differently. So the input and the output are written right here on each arc with a slash in between. So with the Mealy machine, let's say that I reset and begin in state A. If the input is a 1, I go to state B, and the output is 0 based on that input and the previous state. Once I'm in state B, if the input is a 1, the output is a 1 because that's the second 1 that has been detected. And I stay in this state as long as 1s continue to be sent into the input. And the output will continue to stay high, showing that there's a sequence of 1s. As soon as the input changes to 0, the output changes to 0, and we go back to state A. So this is the Mealy machine, showing that the outputs, which are right here, are a function of the present state and the input. So again, you'll see that the one main difference between Mealy and Moore is you will have less states with the Mealy, but the Moore is, in general, is more straightforward and easier to conceptualize than the Mealy. If you look in your textbook, you will see a 3-process template for a general finite state machine. This is a general template. You'll have to adapt it to your application depending on what you're trying to build, but you can reference this in your book as you begin experimenting with your own state machines. You'll notice in the template, it has a type state, and this time it's an enumerated state. The first example that I showed you created a subtype and just set it to be a standard logic vector value. The other way to create your states is to use enumerated states. I'm going to show you an example of that in a few slides. With enumerated states, you literally give each state its state name right here. State A, state B, state C, etc. After you set up your architecture with your state type, you're going to create your signals. You need a present state and a next state for every output that you have. And then you're going to have your state register process, which is going to respond to the clock it's going to determine what should happen if your reset is activated. So you're going to set the present state to an initial state of your choosing. Otherwise, you're going to set the present state to the next state. Your next process will be the process to control the outputs. And you're going to generally use a case statement where you look at each particular scenario for your present state. So your present state could be one of any particular number of values. You look at the present state and you decide what you're going to do based on its value. Then you have the next state process, which determines what the next state should be. So this is your basic 3-process template. I'm going to go back. So your first process is your state register process, where the clock is going to control the next state becoming the present state, as well as what should happen with the reset. And you can make the reset synchronous or asynchronous. It's up to you. Then you have your outputs process, where you determine what the output should be based on your present state. And then you have your next state process, where you determine what the next state should be based on your present state and your inputs. This is just a template. This is not the only way to implement it. This is a starting point if you don't know what you're doing and you need a place to start. In the next example, I'm going to demonstrate how to create a state transition diagram as well as an FSM for a positive edge detector. The purpose of a positive edge detector is to detect a 0 to 1 transition on an input, and that input is called A. Keep in mind there are 2 conditions that must be met in order to detect a 0 to 1 transition on our input A. First, there must be a 0 at a triggering clock edge. Second, there must be a 1 at the next triggering clock edge. So those are the 2 things we have to detect before our output will display a 1, letting us know that a positive edge has been detected. So, when you begin designing a state machine, you have to start with a diagram. You have to have a roadmap, a clear path for what's supposed to happen. You need to define all possible states. You need to define how you move from one state to the next based on your input. Do not start writing code without a roadmap. You need a diagram. You need to know how you're going to get to where you're going. So the first thing you have to do is draw a state diagram. This is the state diagram for a positive edge detector, and it is written in the Moore style. Notice our clear bar gets us into the initial state, state A. So again, from this point, we need to first detect a 0 and then detect a 1. If those 2 events happen in succession, the output should be high. So within state 0, our output is low. What I want to happen is first the input should be a 0 to move us to state B. Once I'm in state B, if the very next input is a 1, I move to state C. And at that point, the output is high, letting me know an edge has been detected, a positive edge. So remember, the clear bar initializes us to state A. From state A, we must first detect a 0 to move to state B, and then detect a 1 to move to state C. Now, you also have to have a contingency for if that doesn't happen. That's why you have all these other arcs on your diagram. If you take a look at state A, let's say that I'm in state A, the output is currently a 0, and I detect a 1. Well, I have to detect a 0 first, and then a 1 in order to detect a positive edge, so I'm going to stay right here in state A. Once I move to state B, that means I've detected a 0. If I'm in state B and I detect another 0, well, I'm staying right here in state B. Because I haven't detected a 1, that would tell me that a positive edge has occurred. So we're going to stay in state B. Once we do enter state C, that means that a 0 and then a 1 was detected in succession, and my output is a 1. What happens if the input from this point is a 0? Go back to state B and wait for another 1. Or, if my input is a 1, I'm starting all the way back at state A, where I have to wait for a 0 and then wait for a 1 in order for the output to be high. So you have to start with a diagram that puts the concept on paper. From that diagram, you can then create a table showing what the present state is going to be, what your input A is going to be in either case, low or high, and what's going to happen, what's the next state, dependent on input A. So with a state machine, generally speaking, you're going to want to draw a diagram first, truth table second, showing what's going to happen. After you write your code, then you're going to refer back to your diagram and your table to verify that it actually is working the way it should be. If you start off with a diagram that's not correct, or if you start off with a truth table that's not correct, your code's not going to correct, because we're actually going to write our code 100% based on this diagram. So make sure that you have your diagram correct first. So here's our diagram, and we're going to implement this into our code now. Beginning with your entity, you have to define your basic inputs and outputs. So we're going to have our input A. That's the input that we're going to be looking at to determine if a positive edge has occurred. Again, you're always going to have a clear and a clock. And then we have one output, A_PE, which will just tell us when a positive edge has been detected, this output will be high. Now let's take a look at the architecture. Here's where we define our type state, and this is what enumerated states means. State A, state B, state C. We can just call it state A, state B, and state C. Our signal, present state and next state, will be of type state. So that means that present state or next state can only ever have a value of state A, state B, or state C. That will literally be their values based on this enumerated type. Now, if you look at the state register, we have a process statement that's going to control what happens when the clock makes a transition or when clear bar is activated. So we can see here that if clear bar is low, then we're going to set the present state to be state A. Again, that matches our diagram. And if we have a rising clock edge, then the present state becomes the next state. So there's our process statement for the state register. Now we're going to have a process for our outputs. Notice that we're going to have a case statement where we look at the present state. When the present state is C, when we make it to state C, the output should be a 1. If we're in any other state, meaning state A or state B, the output should be a 0. Notice that this process simply implements what the output should be based on the present state. That's the definition of a Moore machine. Our next state process right here is going to determine what the next state is based on the present state and input A. So we have a case statement where we look at the present state. If we're in state A, we're going to use our diagram to determine what should happen next. If A is a 0, we move to state B. Otherwise, we stay in state A. If our present state is state B, we're going to determine what's going to happen based off of our diagram. If the input is a 1, we go to state C. Otherwise, we go back to state B. And then we have when others, which basically covers our last case. What if the state is state C? If A is a 0, go back to state B. Otherwise, we're going back to state A. This is pretty much all the code you need to implement this. Hopefully by now it is clear how essential a good picture is, because if this is what you have to go on, it's very clear to see how this code comes about. If you start trying to write code without a picture, you're going to make it a lot harder on yourself. So a good strong picture, a good strong diagram showing every possible state, how you move from one state to another based on the inputs, is going to be your best friend when creating a state machine, because the code flows naturally from your diagram. If you were to simulate this particular piece of code, here's what you would get. Here's your enumerated states. So within a simulation, these don't actually have a value. They literally just stand for state A, state B, state C. But we can see that input A has a positive transition right here. Now remember, our state machine is going to react on every rising edge of the clock, which is why on the next rising edge, our signal goes high, indicating that a positive edge was detected. You can see the same thing right here. A positive edge occurs right here. And on the next rising clock edge, our signal goes high, letting us know that edge was detected. So this is a basic example of how you might implement a finite state machine in the Moore style for a positive edge detector. There's also a way to implement it in the Mealy style. This is the state diagram for the Mealy. I'm not going to go through the code for the Mealy in this lecture. I am going to post the code online so that if you'd like to look at it and compare it to the Moore style, figure out what's the same, what's different, you can do that. But notice with the Mealy machine, you only have 2 states instead of 3. So I definitely encourage you to open up your textbook because the code that I'm going to post online is in your book. Go through that code, compare it to this example. Make sure you understand the difference between a Mealy and a Moore. Make sure you understand the differences in the diagrams as well as how you would write the code. So I'll leave it up to you as an exercise in this particular lecture to figure out the differences between the Mealy and the Moore style of code for this example. So in the last example, we're going to design an elevator controller. We're going to design this from the ground up, and here are the details. We have an elevator that can be at one of 2 floors, ground or first. There's one button that controls the elevator, and it has 2 values, up or down. There are also 2 lights in the elevator that indicate the current floor, red for ground and green for first. And then at each time step, meaning each clock transition, the controller checks the current floor and the current input and changes the floors and the lights applicably. Let's start with a state transition diagram. This will basically convert all of the material with the specifications into a diagram. So we have 2 states. Basically, we're either going to be at the ground floor or we're going to be at the first floor. Our output is going to tell us whether we're at the ground floor and the first floor. Our output is also going to include 2 lights, red and green. If you're on the ground floor, the red should be on, the green should be off. If you're on the first floor, the red should be off and the green should be on. The way we move from one floor to another is by a user input. The user is going to press a button. That button will control whether we go down or up. So if I'm on the first floor and the button press indicates to go up, we stay in this state. If the button press indicates to go down, we go down. Now, since we have a button that controls the elevator and it only has 2 states, you can think of the button as a switch with either a high position or a low position, or you can think of the fact that the button would have to be pressed to be a 1 or not pressed to be a 0, since we have that 1 button. So before we can convert our state diagram into an actual circuit, we need to translate these values up, down, green light on, red light off, etc. We need to translate that into a binary number so that we can represent everything using a state with a unique value. So we're going to decide that ground is 0, down is 0, and off is 0. We're going to decide that first is up as 1, up is 1, and on is 1. When you're the designer of a system like this, sometimes it is up to you to determine these initial values for things like ground floor, first floor, etc. If it's not specifically given to you within the problem, you have to define it. So that's how we're going to define it. Once we do that, we can update our diagram with logic values to represent the ideas of ground floor, first floor, up, down, on, and off. So here's our updated state transition diagram showing our 2 states and how we move between them, as well as what the outputs are. At this point, I challenge you to ask yourself, is this a Mealy machine or a Moore machine? Just based off of the diagram itself, this is a Moore machine, because the outputs are written inside each state bubble. And we can see that the output is dependent on just the present state, not the input itself. So, with this example, we're going to move from the state diagram to a truth table. where we can see the current state, what the input will be for each state, what the next state will be, and how our lights will change. Now that we have a roadmap, we have a pathway for determining what's supposed to happen and how we move within each state, we can write our code. Here's your entity. I've defined 3 inputs: button, the clock, and clear. Remember, clock and clear, you're always going to need. The button is the one user input we have that tells us what floor we're going to. And then we have 3 outputs with this particular example: floor, a red light, and a green light. Those are all outputs, so we have to define those. And now we need our architecture. I decided to create a subtype called state and make that type standard logic, because in this case we only have 2 states with only 2 possible output values, 0 or 1. So I'm just going to make it standard logic. The reason why I am not using enumerated states is because if I want to easily take this code and actually flash it onto my Max 10 board, I need output values that are actual 0s and 1s of type standard logic or standard logic vector. Enumerated types don't necessarily give me an output that I can send to my PLD. So that's why I'm just using a subtype of state. That way I can put this on my Max 10 board very easily, because my actual output values will equate to 0s and 1s. After the subtype creation, we have signals. Now notice I have way more signals than before. That's because I have 3 outputs now. The other examples I showed you, you only had 1 output. If you have 3 outputs, you need to know the present state and the next state for each output. So you'll see that I have a present state for the red light and a next state for the red light, present state for the green light, next state for the green light, present state for the floor, next state for the floor, and they're all of type state. Then I decided to take our definitions that we talked about earlier, create constants where I define state on, state off, state ground level, state first level. So I know that if a light is on, that's a 1. If a light is off, that's a 0. If we're on the ground level, that's a 0. If I'm on the first level, that is a 1. And in this particular implementation, I have 2 processes. The first one is our state register process. Notice that it controls what happens if clear is a 1, where we set our initial states. So the green light will be off, the red light will be on, and will be on the ground floor. If there is a falling edge of the clock, that's when we transfer everything in the state register. So the next state will become the present state when the clock makes a transition. There's our state register process. Then we have our outputs process, where we basically determine what should happen if the button is 1 and if the button is 0. If the button is 1, we know that the red light should have a next state of off because we're going to the first floor. If we're going to the first floor, according to the specifications, the green light should be on, the red light should be off. Here's where we determine the next state. If the button is 0, here's where we determine the next state. Here's where we send the present state to each output that was determined in the port statement in our entity declaration. So these 2 processes will implement our idea of the elevator. And here's our simulation. Here's the clock signal. Here's clear, where we clear everything out and set our initial state. And then the button is pressed right here saying we should go to the first floor, and on each negative transition, the state machine is going to respond. So on this negative transition, we see the floor goes to 1, the green light goes to 1, the red light goes to 0. Right here, we get an indication that the floor should now be floor 0. So on the next negative transition, floor becomes 0, the green light goes off, and the red light comes on. So that's our implementation of the elevator controller. That's pretty much it for this lecture. You will have to implement a state machine for Lab 9. That's the final lab of this course. You will also have to write a state machine for your final exam. So I encourage you to go over some of the practice problems posted, write a few of your own state machines in Quartus, functionally simulate them, make sure you can get them to work, make sure that you can draw a state diagram for a state machine, and take a specification like an elevator controller or a positive edge detector or any number of things, and make sure that you can read a specification for how something works and be able to translate that into a state diagram, both a Mealy machine and a Moore machine. So as always, please reach out to me, email me if you need anything. I am here to help and support you. And like I said, look over the code that I'm going to post online for the example that I showed earlier with the positive edge detector so that you can look at that too. All right, that's the end of this video.